Hello and welcome back. In section 5.4, we work on the definite integral. Time permitting, we may circle back around and do 5.3 near the end of the semester. 5.3 is just an application section, not necessarily new material. So for these next few examples, we're going to consider the function f of x is 1/4 x squared plus 3. And we're going to look at ways to approximate an area involving this function. So area bounded by x equals 1, x equals 4, y equals 0, and f of x. This is sometimes described as the area under the curve. From x is 1 to x is 4. Quick rough sketch of what we're talking about. You recognize this hopefully as a parabola, vertex at 0, 3, and opening up. So x equals 1 to x equals 4, and y equals 0, of course, is the x-axis. So this is what we're looking to approximate. How much area is in this shape? So we have a line segment, a line segment, a line segment, but then we have a curved shape as well. So one way to approximate the area is to use what are called Riemann sums. So the idea is, instead of trying to look at the area underneath this curved shape, we look at a shape we're very familiar with in terms of area, the rectangle. So on this one, we're going to start with the left Riemann sum with 3 rectangles. So the rectangles are going to be of equal width, and I have an interval that's 3 wide, so 3 rectangles split between 3 units. So 1 unit of width, that is our delta x. So the idea here, and I'll kind of just draw a zoomed in version of what I have circled there. So we've got our curve. Left Riemann sum basically means that when I draw my rectangle, I want the left side of the rectangle to determine the height. Then I go over and down. So here is x equals 1, and we're looking at a delta x of 1. So this one starts at 2. Then I'm going to draw a second one starting at 2, and I go up until the left side hits my curve again. Then I finish my rectangle. So that one goes down until the 3. I want to go all the way until I get to 4, though. So our area, I'm basically finding the area of those 3 pieces. And as you can see from our sketch, this is going to be a lower bound. This is going to be less area than is actually under the curve, because we have these small gaps appearing here between the curve and my rectangles. The notation for this, left Riemann sum with 3 rectangles, is written out as L3. So L sub 3, first rectangle has a width of 1 and a height of f of 1. Second rectangle has a width of 1 and a height of f of 2. Last rectangle has a width of 1 and a height of f of 3. So L sub 3 here, the left Riemann sum on 3, we have, let's see, f of 1 would be 3 1/4. 3 1/4 times 1 is 3 1/4. F of 2 would be 2 squared is 4, quarter 4 is 1, 1 and 3 is 4. 4 by 1 is 4, and f of 3, 9/4 is 2 1/4. 2 1/4 plus 3 would be 5 1/4. So L sub 3, let's see, so we have 12 1/2, and that will be in square units because we're discussing an area. So the true area is going to be bigger than 12 1/4 square units. So I'm going to ask you to use the same function, see if you can sketch out and calculate R3. So same function as before. F of x is a quarter of x squared plus 3. Delta x is still 1, and we're still looking for x to be on the interval of 1, 4. So go ahead and pause it, see what you come up with. Okay, I'll start with just sort of a quick rough sketch again. So here's our one that we're starting with. But with R3, I want to use the right side to determine the height of my rectangle. So I'm going to have a little bit of an overcount there. Same thing here. This next one I'll start at 3. That will determine the height of rectangle number 2. And what happens at 4 determines the height of my last rectangle here. So then we're just kind of plugging in. So R sub 3, width of the first rectangle is 1, height of the first rectangle this time is f of 2. Rectangle number 2 is 1 unit wide, height is f of 3. Last rectangle, width is still 1 unit wide from 3 to 4. Height is determined by f of 4. So R sub 3 here. So 2 squared is 4, quarter 4 is 1, 1 and 3 was 4, 4 by 1 is 4. F of 3, that was 9/4, which is 2 1/4 plus 3, 5 1/4 by 1 is 5 1/4. And 4 squared is 16, a quarter 16 is 4. 4 and 3 is 7. So R sub 3 hopefully got to 16 1/4. So notice here, this is an overestimate of the actual area that we're looking for because we have these sections here that are over our curve. So now I know that our true area is bounded below by 12 1/2 square units and bounded above by 16 1/4 square units. So it gives me some idea, but that's still a relatively large margin of error there. If I want a more accurate picture of what's happening, one thing I can do is decrease delta x. So this time I'm going to say let delta x equal 1/2. So we'll keep all the stuff the same as before. So we still have 3 units wide to cover, each being a 1/2 unit wide. I need 6 rectangles. So 3 divided by 1/2, so the width of the interval divided by delta x, the number of rectangles needed. So our width of the interval was 3, delta x was 1/2, so we need 6 rectangles to cover that space. So let's see, let's try out L6 together. And I don't want to squeeze it on there. Let's continue it on the next page so I can get the nice pretty drawing going here. So once again, here's our sort of rough sketch of what's happening with that curve. So here's R1, here's R4 at the end, but this time we're going for 6 rectangles. So go up to 1, f of 1, go over, and now we have something happening at 1.5. At 1.5, go up to the curve, go over and down. At 2, go up to the curve, go over and down 2.5, and continue in that manner. So that guy's at 3, go up and over, and 3.5 is our final of the 6 rectangles. Okay, so a little bit of imagination is needed with pretending that all of those are the same distance apart. They are intended to be mathematically. We operate as if they were. But as you can see, my drawings are not world class. There's a reason I don't work in the art department. So L sub 6, left bound Riemann, left Riemann sum, 6 rectangles. So our unit width this time was 1/2 unit wide, and its height came from f of 1. Next rectangle was also 1/2 unit wide. It got its height from f of 1.5, 3/2. Next one was 1/2 unit wide, f of 2. And we'll just continue this down here. 1/2 unit wide, f of 2.5. 1/2 unit wide, f of 3. 1/2 unit wide, f of 3 1/2. So then we're plugging and chugging on those. So then L6, let's see, we get 13.34375 square units. So after we plug and chug with all of those, so I'm going to ask you to see if you can calculate R6. Same deal, see if you can make a sketch and find R6. Unpause it. Welcome back. So R6, again, I'll make my quick sketch here. So here's my 1, here's my 4. So this time we're doing the rectangles ending at the right side. So this guy will go back to 3.5. This guy will go back to 3 even. This guy will go back to 2.5. This guy will go back to 2 even. This guy will go back to 1.5. And this guy goes back to 1 even. So as you can see, in this particular instance, R6 is also going to be an overestimate. It's not always going to be the case that the left is your lower estimate, the right is your upper estimate. In fact, if we looked at something on the other side of the curve where this were a decreasing function, the left side would be the overestimate, the right side would be an underestimate. And of course, then we also will have functions that are doing both, where we're increasing over some interval, decreasing over another interval. But in this case, we looked at something that over the entire interval, the behavior was the same, where we were increasing over the entire interval. Okay, so this one, our overcount by the 6 little slivers in there. So R sub 6, half unit wide. And the height is found not by 1, but by 1 1/2. Half unit wide on the next one, f of 2. Half unit wide on the third rectangle, height of 2 1/2. Half unit wide, f of 3. Half unit wide, 3 1/2 determines the height, so f of 7/2. And then our 6th and final rectangle, half unit wide, f of 4 units tall. So you do some plugging and chugging in that, and you should come up with 15.21875 square units. So a summary of what we did in those two examples: when we had delta x was 1 and the number of rectangles was 3, and our area was bounded by 12 1/2 in square units and 16 1/4 also in square units. When we change delta x to 1/2, so we cut the width in half, that would double then the number of rectangles. And our bounds got at least a little bit closer together. 13.34375 square units was less than our area, and our area was in turn less than the 15.21875 square units in our upper bound. So our lower bound moved in, our upper bound moved in. We have a more narrow interval. And that's the idea with these, is the more rectangles we make, the closer we would get to the actual picture. As we make more and more rectangles, finer and finer rectangles, the amount of error would just keep dropping and dropping until it gets on an interval that we're comfortable with. So you can just kind of decide how close in do you want to get. Do you want to get within 1/10 of a unit? Do you want to go within 1/100th of a unit, etc.? How close do you want to go? Now we also have the option of using midpoints instead. So the general setup for a Riemann sum, S sub n. So this is not an integral, this is a capital letter S, not an integral. S sub n, f of c sub 1 times delta x plus f of c sub 2 times delta x. And you do that until you have your c sub nth times delta x. So if we keep our previous example, and I want to find s sub 3 with c sub I, midpoint of the ith interval. So let me sketch what I'm talking about. Same goal as before. We're approximating the area from 1 to 4 above the x-axis and below our curve. Only this time we're still drawing our 3 rectangles. So here's our 1, here's our 4, so we're going to have something happening at 2 and 3. But instead of using the left side or the right side to determine the height, we go with the height of the middle to make our rectangle, and we have a little under and a little bit over. Same thing on this one. Go to the middle. We'll have a little bit of an overestimate on one end of it, a little underestimate on the other side. So my first rectangle is 1 unit wide. Its height would be f of 3/2. Second rectangle is still 1 unit wide, height of f of 5/2. And our final rectangle, still 1 unit wide, its height f of 3.5 would be 7/2. So S sub 3, 14.1875. So I'm going to ask you all to pause it and see if you can find S sub 6, same definition for CI. Okay, so I'm going to make my drawing a little bit on the larger side just because this has a lot of rectangles going. So here's our 1, here's our 4. If we're looking for S6, that means we want 6 rectangles. Total width that we have to work with is 3, so each one is going to be a 1/2 unit wide. Here's our 2 and our 3. So the midpoint of 1 and 1.5 is 1 1/4. Between 1.5 and 2, 1 3/4 would be our midpoint for this guy. And again, a little under and a little over. Between 2 and 2.5, we have 2 1/4 for our height here, for our x value that's used to find the height of the rectangle. Between 2.5 and 3, there's our 2 3/4. A little bit of an overestimate, a little bit of an underestimate, and so on. So between 3 and 3.5, we have 3 1/4. We'll use that to guide our height. And then our last rectangle is between 3.5 and 4, so 3 3/4 is the x value that we use to pick out our final height. So S sub 6, each of these is a 1/2 unit wide, so 1/2 by f of 5/4 plus 1/2 f of 7/4 plus half by f of 9/4 plus half by f of 11/4 plus half by f of 13/4 plus half f of 15/4. So S sub 6, once you plug and chug all those, you should get 14.2343 in square units. So we'll see in our next section exactly what the area is and how close we are to it. So next up, though, we look at a little bit of notation. Limit, our friend the limit is coming back. Limit as n goes to infinity, the sum from I equals 1 to n of f of c sub I delta x. So this is, the sigma is saying sum. So we're adding up. Notice these are how we found the area of each rectangle. So add all of your rectangles together is really all this scary looking notation is saying. So this limit as n goes to infinity basically says draw more and more rectangles. So we've been drawing 3 of them, 6 of them. This is saying draw 100 of them, draw 1,000 of them, draw 10 billion of them. Let n go to infinity. Now that would give us the same result if we looked at it a different way. Let delta x go to 0. Let the width of each rectangle start approaching 0. If you're squeezing more and more rectangles into the same space, the width is getting smaller. So same idea, either number of rectangles goes to infinity or the width of the rectangle goes to 0. Both of those are equal to what we would call the integral from a to b of f of x times dx. That looks awful familiar. That we've seen in another section. So a few properties of these definite integrals. So here I should make one more statement about a and b. So a is the left x value, b is the right x value. So for example, in that last one, we were going from 1 to 4. How far left do you go? How far right do you go? So a couple of properties of these things. Integral from a to a of f of x times dx. If your left and right endpoints are the same, instead of a rectangle, you've made a line segment. The area of that is 0. The integral from a to b of f of x times dx is the opposite of the integral from b to a of f of x times dx. So if you accidentally went from the right bound to the left bound, you would have an opposite value come out. Usual rules that applied with the indefinite integrals still apply to the definite integrals. So for example, the integral from a to b of k f of x dx is k times the integral from a to b of f of x dx. So k here is just some arbitrary constant. Sum and difference rules apply as usual. So integral from a to b of f of x plus or minus g of x dx is the same thing you would get splitting it up into two pieces. You just keep your same endpoints. And this would be a plus or minus here, whatever we had in the original. Now, one important tool that you didn't see before as far as integrals, let's say that a is our left bound here, b is our right bound, and then c is somewhere on that interval. The integral from a to b of f of x dx, I can split it into pieces. Integral from a to c of f of x times dx plus integral from c to b of f of x times dx. That is sometimes necessary. We'll see how and why a little bit later on. So let's see what I want to try. We'll do a few givens. So integral from 0 to 5 of x dx. Let's say that that's known to be 12 1/2, and that the integral from 0 to 3 of x squared times dx is known to be 9, and that the integral from 3 to 5 of x squared times dx is known to be 3 1/4. Sorry, not 3 1/4, 32 2/3. So if they give us this information, they could ask us, for example, then to find, let's say the integral from 0 to 5 of 7x squared plus 10x quantity times dx. So this one, we'll have to do a little bit of breaking up of that. So the 7 I'll put outside, integral from 0 to 5 of x squared times dx. I'll do the same thing with the 10. 0 to 5 of x times dx. So let's see, integral from 0 to 5 of x dx, we do have a number for that. We don't have one single number for integral from 0 to 5. But we do have 0 to 3 as well as 3 to 5. We can use this property. So then this is 7 times the integral from 0 to 3 of our x squared times dx plus the integral from, then pick it up from 3 to 5 of x squared dx. That one also is going to get multiplied by 7, or you could have used a single 7 and put those in brackets. Plus 10 times the integral from 0 to 5 of x dx. So you have 7 times, and then just a little bit of a substitution game. So 0 to 3 of x squared dx is 9. 7 times integral from 3 to 5 of x squared dx, 32 2/3. Plus 10 times 12 and 1/2. So plugging and chugging on that, we should get 291 2/3. So we'll see how to split those up and why we would split them up in the next section. All right, so some problems to try out. This was in section 5.4. So remember 5.4, 5.3, just a couple of applications. We'll come back if we have time. They're nice application problems, but it's more important we cover the topics that we need to get through. So 718 all. 23 to 53 on the odds is what I would recommend. If you have any questions, please get in touch. Otherwise, I will see you next time. Stay safe out there.